Hello, Calculus 3 students. Today we're going to just talk a little bit more about partial derivatives and some of the things that you can do with them. And what we're really going to be looking at is tangent planes and differentials. So one of the ways that we use derivatives way back in the beginning of, regular calculus is we use derivatives to create tangent lines. Well, if I'm in multivariable calculus, I have a surface, and instead of a tangent line to a surface, I'm going to use a post-it note, I have a tangent plane that balances on my surface like that. So if I need to write the equation of a plane, I need to know kind of the slope in the x, y, and z direction to create coefficients for x, y, and z. And the nice thing here is those coefficients just come from a derivative, just like we're used to. Okay, so assuming f is differentiable, so assuming you have a tangent plane at a point AB, and technically, I guess you could say f would be differentiable at the point ABC, where c would be the z value. The equation of the tangent plane is as follows. F sub x of AB times x minus a plus f sub y of AB times y minus b minus parentheses z minus c. Or we usually write it in z equals form so that we have a surface that's a function and then a tangent plane that's written as a function. And if you write it that way, it's just going to be the z value, so like z sub 0 plus the partial derivative with respect to x times x minus a plus the partial derivative with respect to y times y minus b. And really, I just rambled on for a while, but it makes more sense when you just do it. So we're going to just do it. Find an equation of the plane tangent to z equals x squared plus y squared at the point 3, 4. Okay, fine. So the first thing I'm going to need is honestly the z value. So if I'm at the point 3, 4, z evaluated at the point 3, 4 is going to be 3 squared plus 4 squared, which is 9 plus 16 is 25. Okay. And then I need the slope in the direction of x and y. I need the rate of change of z with respect to x and the rate of change of z with respect to y. So I'm going to find a z to x, and that's 2x. And I'm going to find a z to y, and that's 2y. And a z to x, evaluated at 3, 4, is going to be 6. To z to y, evaluated at 3, 4, is going to be 8. And so the tangent plane equation is simply z equals the initial z value plus the derivative with respect to x times x minus the initial point plus the derivative with respect to y times y minus the initial point. And there it is. That's it. All right, and if you want to see, Mrs. Vibber, I wonder what that looks like. I can show you what that looks like, or maybe not so much me as GeoGebra. So let me pull up some GeoGebra here. And our first equation, eventually, was z equals x squared plus y squared, which is this happy looking parabola right here. And then our equation was z equals, for the tangent line, 25 plus 6x minus 3 plus 8y minus 4. And right now, I don't really see it touching, but you know why? That's because we're zoomed in too much. So I am going to zoom out a bit. Oh, I still can't see it because z isn't up to 25 yet, so I'm going to zoom out a little bit. There we go. And now you can kind of see if I tilt it. Okay. There's my tangent plane that just barely glances up against the edge of this. Okay. Ta-da. Cool. So let's go back. And I have everything I need here. Glorious. All right, so let's do another one. Find an equation of the tangent plane to z equals y times e to the x over y. Well, you know what? Let me put that in GeoGebra also here. So let me clear this out and say z equals y times e to the x divided by y. Yep. Ooh, that looks fun. What a nifty graph that is. And we want to find the tangent plane at 1, 1e. So I'm going to just put in 1, 1e. Okay, so that's, definitely on my curve. Cool. Now I want to make my tangent plane. Okay, let's do it. So if I want an equation of that tangent plane, let's see. I have the z coordinate already, so I'm good to go there. Now I need my partial derivatives. So I need dz dx. Well, let's see. That y is like a coefficient, and the derivative of e to the x divided by y is going to be e to the x divided by y times the derivative of x divided by y, where x is a variable and y is a constant, and the derivative of that is going to be 1 over y. So dz to x is e to the x divided by y, and dz to x at the point 1, 1e is going to be e to the 1 over 1, which is still e. And then if I want dz to y, I'm going to need a product rule because it's a y thing times another y thing. So I have the first times the derivative of the second. Okay, so e to the x over y's derivative would be itself times the derivative of the exponent. And the derivative of x over y with respect to y is going to be negative x over y squared. So there's the first times the derivative of the second plus the second times the derivative of the first. And really that's going to be negative x e to the x over y divided by y plus e to the x over y. And if we evaluate that at 1, 1, I'm going to get negative e plus e equals 0. Wow, that was a lot of work for a 0, but I don't mind zeros, so I'll take it. All right, so I have my derivative with respect to x. I have my derivative with respect to y. So my tangent plane is going to be z equals the initial z value plus e times x minus 1 plus 0 times y minus 1. And yes, I know it's ridiculous to write that out. So I'm going to write it as z equals e plus ex. Nope, not e to the x. My hand just wanted to write e to the x. Ex minus e, which is really z equals ex. What a fun tangent line that is. Z equals ex. Let's see if that makes sense. Z equals e times x. Yeah, looks pretty good to me. So there's my tangent plane, I should say. All right, so find the equation of the tangent plane to this last thing. Okay, I'm going to stop graphing them just because it's taking a lot more time than it needs to. So when we come down here and do our tangent plane, I'm just going to do it. So how about you do it and I'll stay silent. So I ended up with z equals 6y minus 9 as my tangent plane here. And you can either simplify it or not simplify it. What I did in these last two examples is I simplified the tangent plane just because I saw things that would combine and I was happy to do so. After tangent planes, we're going to talk about something called the differential. And really what the differential is estimating via the tangent plane. It's linearizing a surface. If you remember again from last year in two-dimensional calculus, we use tangent lines to estimate things quite a bit. And then eventually we used, if you remember, Taylor series and Maclaurin series to estimate things. All right, differentials are just that, and it's a linearization of a surface. So we say, okay, if my surface looks like that, my surface looks like this, and I have a tangent, I could use the points on this tangent plane to estimate points on the surface. All right, that's really kind of what a differential is doing. So if you look at the total differential, a differential is dx, which is really an infinitesimally small delta x, and dy. If you want the total differential, what you're really looking for is dz, meaning what happens if x changes a little bit and y changes a little bit, what happens to z? That's what a total differential is. And what you end up finding out is dz is equal to the derivative with respect to x times dx plus the derivative with respect to y times dy. Okay? In other words, the slope times the change in x plus the slope times the change in y. Now, I'm using the word slope very vaguely here. When I say slope, I mean f sub x is the slope of z with respect to x. All right? So, it says, think about the connection between the equation of the differential and the equation of the tangent plane. Well, my tangent plane was z equals basically z sub 0 plus f sub x times x minus a plus f sub y times y minus b. Well, if I subtract z sub 0 from both sides, I get z minus z sub 0, which could be called delta z, which if it's a small enough value, delta z is really dz. Okay, so then that would be canceled out. And then over here I have f sub x times x minus a. Well, x minus something is a change in x, and y minus something is a change in y. So this is really f sub x times dx plus f sub y times dy. Your tangent plane is really a formula for the total differential. That's it. Okay. Paraphrase total differential. That is the estimated change in z when given small changes in x and y using the tangent plane as a linearization. That's really what we're doing. All right, not much left. So this whole lesson is really the same thing. It's just tangent planes over and over again. So this thing says calculate the total differential for z at the point 1, 0 using step sizes of delta x is 0.01 and delta y is negative 0.02. Sorry for the terrible line return there. Well, okay, I'm going to use the total differential formula. dz equals f sub x times dx plus f sub y times dy. All right, so I need f sub x and f sub y then. So dz dx is really just e to the negative y. And dz dy is going to be negative x e to the negative y. And I'm supposed to find those values at the point 1, 0. So dz dx at 1, 0 is going to be 1. And dz dy at 1, 0 is going to be negative 1. And so dz is going to be the derivative with respect to x, which is 1, times the change in x, which is 0.01, plus f sub y, which is negative 1, times the derivative, times the change in y, which is negative 0.02. So I have 0.01 plus 0.02, which is 0.03. Now, what does that mean? It means if you start at the point 1, 0, which is, by the way, if I plug that into the original, would be the point 1, 0, 1. If I go from 1, 0 and go in the positive x direction 1/100th and in the negative y direction 2/100ths, I can expect my z to increase by 0.03. So I can estimate that I'm nearly at the z value of 1.03. Calculate the total differential of the Cobb-Douglas function, we'll talk more about that in other times, of P of LK, that's production based on labor and capital, at the point 101, where delta L is -5 and delta K is 0.25. Explain your answer in context. Okay, so the Cobb-Douglas function is really the Cobb-Douglas production function, where P is your production, L is labor force, and K is capital. I think that's capital with an A. Is it an A? Is it an O? I always forget. I think capital in terms of money is an A. It's one of those things that never sticks in my noggin. All right. I want the total differential of the Cobb-Douglas production function. So really, I want dP is going to be P sub L times delta L plus P sub K times delta K. Or if I don't want to write delta L and delta K, really I'm using the differentials, dL and dK. I don't care how you write it. Fine, I need P sub L and P sub K. All right, so here's my function. P is 1.01 L to the 0.25, K to the 0.75. So if I want P sub L, that's the derivative with respect to L, so 1.01 K to the 0.75 would all be like a coefficient. And then the derivative of L to the 0.25, well, that's a letter raised to a number. I'm just going to use the power rule. So I'm going to bring down the power and then reduce it by 1. So there's P sub L. And P sub K would be 1.01 L to the 0.25 times 0.75 K to the negative 0.25. Just another product rule. I'm supposed to evaluate those at 101. So P sub L at 101 is going to be 1.01 times K, that's the second one, 1 to the 0.75, times 0.25 times 100 to the negative 0.75. All right, fine. And P sub K at 101 is 1.01 times L to the 0.25 times 0.75 K to the negative 0.25. All right, let's see. I really want to know what those are as decimals. So I am going to go to, you know where I'm going to go? I'm going to go to Desmos, because Desmos is a calculator I can use. And here it comes. And I've got 1.01 times a quarter times 100 to the negative 0.75. 1.01 times a quarter times 100 to the negative 0.75. And that's 0.00798. 0.00798. And then I have 1.01, 100 to the quarter times 3/4. All right. 1.01 times 100 to a quarter times 3/4. 2.395. Okay. So there's my partials. And so if I want to know my change in production, I'm going to do 0.00798 times the change in labor, which was 100, plus 2.395 times my change in capital, which is 1. And then let's see. So 0.00798 times 100 plus 2.395 times 1 is 3.193. And I'm supposed to explain that in context. So what that means is if you start, oh, Mrs. Vibber, See, I'm going to leave this error in here because in case you guys ever make it, you're probably already yelling, Mrs. Pepper, you did that wrong. I put in 101 as a DL and DK. That's not what those are. 101 are L and K. Here's delta L and delta K. Silly me. Delta L is -5. My apologies. And delta K is 0.25. There we go. So let's try that again. 0.00798 times -5 plus 2.395 divided by 4, because it's times a quarter. There we go. 0.55885. All right. And in a very simplistic context, what does this really mean? It means if you start with 100 workers and let's say $1 million in capital, all right, you start with 100 workers and $1 million in capital, you have a certain production level. If you decrease your labor force by 5 people and then add $250,000 back into the pool, you can expect your production to go up by 0.55885. So whatever your production is measured in, whether it's measured in profit, whether it's measured in, widgets that you produce, whatever it is, if you decrease labor by 5 and increase capital by 1/4, your production will increase by around 1/2. All right. I am done for the day. I hope everybody's having a glorious day on their own. Sorry for the dinging bells in the background. We'll talk again soon.